বস্তু এটা শ্বেয়াৰ কৰিছোঁ আপোনাক SF DUSC গ্ৰুপত শ্বেয়াৰ কৰিছোঁ এতিয়া লিংক হয় এটা আৰু আমাৰ টক ছেশ্যনটো লিংক হয় য়েছ ষ্টাৰ্ট কৰোঁ তাৰ আৰু লাগে 6-5 ষ্টাৰ্ট কৰোঁ ঠিক আছে হৈ গ'ল দিয়া কামটো এই কিবা টক ছেশ্যনটো জইন কৰিব আৰু এই জইন কৰিব দিয়াচোন বেলেগ কেইটাকো লিংকটো শ্বেয়াৰ কৰি দিবা DUSC গ্ৰুপত
Hello, am I audible? Just someone confirm it in the chat box. Okay, we'll start our session. So almost 60 participants have already joined. So we'll start now. So a very good evening to everyone here. I am Abhilash Biswas from the Department of Physics. I, on behalf of the team of Insignis, I'll be your host for this session. And we welcome and thank everyone who have joined on this virtual platform, and also to the audience who is through YouTube. I will request to share the link if someone is still not able to join or doesn't have the link. So the title or the topic of our session will be "The Future is Not Solid, Soft Matter Physics," and our speaker has already joined the session. We have with us Sri Noman Hanipur Buratha, who is currently pursuing PhD in IIT Gandhinagar, and he is an alumni of Tezpur University. He has done his master's from the Department of Physics here. And so, thank you, Nomenda, for accepting our invitation and giving us your time.
Hi. Very good evening to all.
Just a little bit, I am not able to hear the first. Hello?
Yeah, can you hear me now?
Just a minute. Hello? Yeah.
Yeah.
Yeah, I can hear you.
Okay. Cool.
I guess I have some technical issues. Just check me. Hello. Nomenda, I
Yes,
think
yes, Abhilash.
okay. I'm getting your voice. Okay. So sorry for that. We'll start the session. So Nomenda, take the platform. Uh, start. We can start.
So, shall I start? Shall I start?
Yes.
I'm still. I think I have been.
Uh, is it a problem at my end? Like, is anybody else able to hear me?
Yeah, I'm not getting the voice.
Am I audible to everybody? Okay. Hmm.
Okay. You can carry on.
Okay. So, a very good evening to everybody. I have been associated with Technical University since long time, and it had a positive impact on me. I got good amount of exposure. I made lifelong connections, and it's only because of the Technical University I got interested in soft matter due to chain of events. I was a quantum electronics guy, and now I'm doing soft matter, and I really like it. And so I'm very surprised to see such a huge number of people here. Are you people not tired after the classes? Like, I'm just asking. Anybody can answer. Anybody can respond. Uh, am I audible?
Yes. You are audible.
Yes, I'm just asking. Like, it's, I'm surprised to such a huge number of participants here because I was expecting only 20, 30. It's almost double my expectation. Seems like nobody's tired after the classes. I used to get pretty tired at this time. Okay, so I will just start my presentation. Before that, I just letting people know that language should not be a barrier. So if anybody has any questions, if I don't make myself clear, please ask me in any language you want. I will try to answer you. And I kind of feel that it's my responsibility to make things clear to you. So please help me in that. I'll just share my screen now. Give me a moment. I hope you can see my screen now.
Yeah, it's visible.
Yeah. So Abhilash keeps saying something in between because I don't know if the connection gets get lost and
Sure.
I'll
Yes.
speaking to nobody. Uh,
Okay.
okay. Uh, so the title you saw in the posters was a clickbait. I say that future is not solid. It doesn't mean anything. So so for time, the title is of the presentation is soft matter physics, physics at single particle level. And by the end of this talk, I will try to justify this second part, physics at single particle level. And I promise that I will explain you what are all of these videos. These are colloids, this is crystallization happening. This is a lizard swimming in sand, and this is some kind of soft robot. Uh, I promise you that I will touch every one of these. So before I formally start, I would like to start with a conundrum or an anecdote that we all are made up of atoms, and what we do is that we study atoms. So isn't it that a group of atoms are studying the atoms? So this thought has always stuck me, and I have been searching for this answer, like how a group of atoms study itself. So what are the emerging properties? So, and that's why I'm into physics. And the fundamental goal of physics is that given an initial condition, suppose these are some particles, and I know the rules of the game. I know that what are the rules of the interaction. Suppose the interactions are gravitational interactions only. The fundamental goal is to comment on the dynamics of the system, comment on what will happen in the future, how the system will evolve. So in a sense, is just connecting the structure with the dynamics. There is nothing else in the physics. If I have a system and if I know its initial condition, I know the rules of the game, and if I'm able to comment on the evolution of the system, I'm done. My job as a physicist here is done. So this problem is simple for typical systems. Suppose if I have a projectile motion, I know my initial velocity, I know my gravity, and I can just use the laws of kinematics, and I can predict the future motion of time evolution of the particle. In this case, it's a parabolic path. If I have charged particle between a capacitor, I know the laws of electrostatics, and I can still comment on this evolution. But when things become complicated as you increase the number of particles. So suppose you have billions of particles in a container, billions of people, in a jar you have billions of gas molecules. In that case, this it becomes complicated. Also, if I have complex interaction rules, so we as a people, we also interact with people, but the interaction is not simple. Unlike an atomic system where the laws are almost from the electrostatics, or if I have a planetary system, the laws are gravitational. In case of peoples, and I will show you some other examples in which the rules of engagement can be very complicated. Also, if I just play with the shape of this projectile, things will again become complicated. If it were an ellipsoid, and if I consider the air drag, it will also become complicated. So let's look at the bigger picture. So as I said that we are made up of atoms and we are studying atoms. So let me put it in another way. So this is the hierarchical structure of any matter. I am showing the structure of a human body of us. It could be extended to other stuffs. So these are what you see here. Spheres are atoms or molecules. These make up of the proteins, and these proteins make up some structures in your cell. And in a cell, there are multiple structures, right? And these structures interact with each other. And these are the complicated interactions, because you see I know about the atomic interactions. The interactions change as I change my length scale. Now these cells interact with each other and form something called as tissues. These tissues also interact with each other tissues, form organs like your heart, also your brain, with which you are able to think now. So at a different level, the individual atoms and molecules, the individual building blocks are combining to build something bigger. And at each level, the energy scale is different. And that's where the soft matter comes in. So typically in condensed matter phases, so if I have a condensed matter, it means that I have some kind of attraction, and because of which things are staying together. So typically, if I consider an elemental crystal, the typical length scale, by length scale I mean the separation between the atoms, is around 1 angstrom, that is 10 to the power minus 10 meter. And if I were to calculate the interaction energy, now how did I calculate the interaction energy? You can just consider two ions separated by a distance 1 angstrom. If you calculate that, you will find the energy is of the order of 10 eV. And if I convert it to in terms of kVT, here T is my room temperature, so it's around 100 times my room temperature. So the room temperature, the energy from the thermal energy is not able to dissociate my system. Also, if I just calculate the energy density, so what is my energy density? Energy density is just the interaction energy per unit volume. Here my volume comes from the length scale, so energy density is around 10 to the power 12 joules per meter cube, and I can find the Young's modulus. So Young modulus is also of the order of 10 to the power 12 Newton per meter square. It means that I need around giganewton per meter square of pressure to deform something, right? It's a huge pressure. But If I consider now supramolecular structures, what are supramolecular structures? If I just take these building blocks and I keep building larger and larger structures, and I suppose the larger structures has a length scale of 10 to the power minus 6 meter, that is 1 micron. So these building blocks made something bigger, and these bigger stuffs are interacting, like the cells in your body, the RBCs in your blood. They are of the order of micron. And if I now calculate the interaction energy, it comes out to be less, but not very less. These are of the order of kVt. But if I calculate the energy density, it's around 10 to the power minus 2 joule per meter cube, which will give me an Young's modulus, or the pressure required to deform is very less. That is 0.01 Newton per meter square. So just by touching something soft, just by touching my skin, I can deform it. So that's the crux, the difference between the typical condensed matter versus soft matter. And if you look around, you'll find that most of the stuffs the nature has built are soft. The skins are soft, the organs are soft.
The magnitude is very large compared to both the systems.
So here the Young modulus is 10 to the power 12 gigapascals. Sorry, it's in the range of gigapascals.
Yes, yes.
So if I have to break one iron rod, it will take a lot of, lot of force. I need to be very muscular to break it. But if I were to break somebody's hand, I won't do it. That will take very less amount of
Yes.
energy. Yeah. In fact, the room temperature is sufficient. So you may have seen the chocolates are melting in summer. Chocolate is because these are soft systems. Here you will find inside chocolates you will find supramolecular structures. So molecules combining to form structures, and these structures again arrange among themselves. So here if you see that if I were to bend an iron, I need to hit it with a hammer. But these are jellies. So if I just drop it from some height, they will get deformed. So that's the crux of the soft matter. So if anybody has any questions up until now? Okay, let's move on. So
Feel free to ask question in the chat box, or you can ask question during the sessions also. We'll address those things.
okay,
Okay, you
moving
can
on.
carry on.
Yeah. So these are some of the typical examples. So your toothpaste is toothpaste solid or liquid? The boundary is not clear. In case of condensed matter system, is very clear. So like this pen, this is solid. I know. Here I have water. It can flow, right? So anything that can flow is liquid. It cannot flow, so it's solid. But toothpaste, if you unless if I give it a pressure, it becomes a liquid. If I don't give it a pressure, it behaves like a solid, right? These are styrofoams. These are polymers. So all of the polymers are actually soft matter. Microbes, of course, these are soft matter systems. So if you just give them a little pressure, they may die. And these are colloids. So the colloids, I work on colloids. So these are the different types of soft matter system. I work on colloids for a very specific reason, which I will explain. So colloids are basically micron-sized particles suspended in some kind of solvent. It could be water. So an example of colloid could be your milk. Here the proteins and fats are suspended in water. And so in all of the systems, you'll find some kind of supramolecular structures. Now, uh, now there's a question: is sand solid or liquid? The answer is sand can behave as solid as well as liquid, depending on at what force you are imparting it. So sand has a property called viscoelastic property. So here you can see a lizard can swim through sand. But if somebody is able to swim through sand, it means it is liquid.
Yes, yes.
Yeah. But also if you can make mega structures on sand, like Burj Khalifa, it is built on sand. How? So sand is viscoelastic. What I mean by viscoelastic is that if you apply pressure very quickly, it behaves as solid. But if you apply pressure gently, it behaves as liquid. So this lizard, by moving its muscle very fast, it is able to swim. It is just like a bulletproof jacket. So bulletproof jackets are actually just like sand. If you hit it very hard, it becomes solid instantaneously. So, and the applications, I will not go towards the application part much because I am a physicist. My job is to, you know, given a structure to predict the dynamics. So these are soft robots, and these can be used for surgeries because our tissues are very delicate. So we need also delicate hands to handle them. These can, so if you were to, if you make a robot to hold a grape, it will, there's high chance that it will break it, it will tear it. But these kind of soft robots can hold delicate stuffs. It can use to kind of sample your. If I just put my hand inside, it can sample my hand, right? It can. Uh, so hello, is my
Yes, yes.
yeah. Sorry, just to adjust here. So what I was saying is that if I just had some kind of structure here, if I want to uh, model it somehow, so I can just put inside a soft robot and it will squeeze on it, and
Yes.
depending on how long it takes to squeeze a certain part, I can quantify the structure, the action structure of uh, this material. So as I said, I work on colloids. It's for a very specific reason. So colloid is a soft matter system, but colloid can also act as a model system for my condensed matter phases. So in condensed matter,
Uh,
yeah,
Nomenda, I just want to ask one question.
just call me Norman.
Okay, no, see, it's fine. So I just want to ask that why, like microbes, it's a living thing. How it falls on the soft matter system?
To characterize soft matter, I need two things. One is the energy scale,
Yes.
the what are the bonding energy between them, and second the length scale. So if you look at a microbe, the length scale is typically micron size.
Okay.
Okay, and then around, if I go back to my previous slides, I need these. So this is the characteristic of soft matter system. The interaction energy should be of the order of my room temperature, so that room temperature can deform them. So the bacteria are moving, right? So these are actually performing Brownian motions.
Oh, okay.
Yeah. So they have their individual directionality. On top of that, they have Brownian motions. So if I can just move along, if I just move out of this room, it's very easy for me. But for bacteria, they're competing against the room temperature, the thermal energy, because
So
at
like,
one point, yeah,
yeah, so like their movement is restricted by the Brownian motion that we
yeah,
can we say it like that.
yeah. So the their swimming method. So how do I swim? If I just move my hands like this, I can swim. But in case of bacteria, the swimming mechanism is quite different.
Okay. Okay.
Okay. So yeah, anything that has energy density of this order can be classified as hard condensed matter. Anything that has very low Young modulus or energy density is soft condensed matter. I exactly do not know where is the interface lies. What is the thin line that divides soft from hard matter? But these are the two extreme cases I'm showing you.
Okay. So we also have two questions on the chat box.
Okay.
So let me dictate it for you. So Pulkit has asked, are supramolecular molecules made up of other larger molecules?
Supramolecular typically means made up of molecules, but yes, uh, you can use supramolecular structures to build something called as supramolecular. I don't know if this term really exists, but you can make mesoscopic structures. So when I say mesoscopic, it means the scale is from in between micron to centimeter scale. So did I answer the? Did I make myself clear?
So Pulkit, you can just type on the chat box that if it's clear. Yeah, it's clear for him.
Okay.
So we have one more question from Abhishek.
Huh.
He has asked, Sir, non-Newtonian fluid is a soft matter. Is it a soft matter?
Non-Newtonian fluids are classic examples of soft matter. So if you have cornstarch, if you heat it very hard, they becomes like the viscosity rate is becomes very hard instantaneously. But if you put your hands really slow, you can go down the container.
Yes, yes. So is it
These are
clear
very
for Abhishek?
okay.
Yes, carry on. You can carry on.
So I say that I work on colloids for a specific reason because colloids, although are soft mattered, I can use them to model atomic systems as well. So in atomic system, what happens is that the length scale is around 1 Armstrong. The atoms are very small, of the order of Armstrong to nanometers. The molecules, if I consider molecules, so it means that they're moving very fast, right? So using electron microscopy, I can see the atoms, but I cannot track the atoms. It's a technological limitations that we have till now. That although using electron microscopy, somehow I can see a blurred picture of the atoms, but if you have to track how it's moving, I cannot do that. Colors
Yes.
come, yeah, colors come here. So colors are large molecules, right? And if I just write the free energy equation, uh, consider the colors that the colors that I work with have Harshway interaction. It means that if the colors are separated, they don't see each other. There is no interactions. There is no 1 by r square dependent on 1 by r cube dependent. They just don't feel each other. If they touch, they're feeling each other. They will repel. That's simple. And that's my Harshway potential here. So here my potential is 0. Here it is very high. If I write the free energy equation, my U will become 0 because it's hard sphere, they don't see each other. And the phase space becomes entirely governed by this entropy term. And in my colloids, I can get the phases of the condensed matter. So what are the typical phases of condensed matter? Liquid, crystal, and gases, and also the glass.
Hmm.
So here in colloids, if I just change the number of particles packed in a given region, if less number of particles are packed, I'll get a fluid phase. If I start packing more and more particles, they have to go arrange themselves, right? And to arrange themselves, they will ultimately form a crystal because in crystal the packing efficiency is maximum, right?
Yes.
Yeah. So here in colloids, in a condensed matter system, you can change your temperature. You can grow from solid to liquid by changing temperature. But in a colloidal system, you go from liquid to solid by increasing your area fraction, the number of particles packed in a region. So here I established that my colloids can also show the same phase of condensed matter. Now, what's the advantage now? So these are colloids, these are micron size. It means that these are larger particles and they will move slowly. So the typical relaxation time for colloids is 1 millisecond to 1 second. So I can just use this microscope. I can just use this microscope to see them. So they're big enough to see and they're slow enough to track. I can track individual colloids. So when I said in my title that I will be telling you about the physics at single particle level, that's what I mean.
Like, what's the significance of tracking those?
Tracking those, suppose I will show you in a couple of next slides.
Okay.
Okay. So tracking them, okay, let me answer it quickly. So if I have particles, if I had some atoms here, right?
Hmm.
And if I had two different kind of atoms, how they're interacting, to know that I need to track it, right?
By their
Otherwise,
motion, we can.
by the motion or somehow, typically what we do is that we write codes, we write softwares to track individual particles, and from their trajectory you can comment on some physics. I will show you.
All right.
So colloid has these direct visualization of crystallization has helped us answer some of the unsolved problems like crystallization, how crystallization happened. Nobody knew in the, it's not possible to actually see crystallization happen, that I'll show. It's not actually easy to see how self-assembly, how these molecular structures uh, assembled together and the flow behavior of particles. So these are my two of my research that I've been doing. This is done, is sent for publication, and this is what I'm doing right now. So here these particles are just colloids. They're moving in 2D, and I wanted to see uh, how the dynamics in 3D is different than the is how the dynamics in 2D is different than that of 3D. So what we did is that we did the experiment, we tracked the particles, and from the tracked particles, I had the location of each of the colloids, right? And then I can invoke the rules of statistical mechanics
Okay.
and find the governing equations. And this is something interesting I will show you. So you can see some colloids are there. So basically the system is that upper se particles are raining down, they're coming on the surface, and they're talking to each other, and they're forming a crystal. I'll play the video, watch it carefully. So the particles from the top are coming down, and these blue particles are some special kind of particles. You can see that the crystallization is happening in real time. And that's the beauty of using colloids. You can visualize that,
Yes,
directly
yes,
visualize.
yes.
Yeah.
Like they are forming in like lumps, not in a
Yeah, so
ordered way.
forming crystal. So how crystallization happens actually? I can answer from this video itself. What are the
What are the
structures? So
structure?
you can see that these are forming hexagonal structures, right?
Yes.
Yeah. So in this experiment, we wanted to study like what are the role of these impurity atoms. You can see that almost all of these impurity atoms, near these impurity atoms, they are forming clusters. So the application is that if you have a semiconductor manufacturing array and you are trying to build a chip, an IC, so you are using epitaxy, molecular beam epitaxy. If there was some kind of impurity, what would be its impact?
Okay.
So these are typical colloid experiment system you can see in the back. I will just play the video. So what is coming? So this is the screen. It's connected to a camera, and we wanted to know what happens if you just share a crystal. Share a crystal means if you make a crystal flow. So you can see that it's flowing. These crystals are flowing, and let's say a microscope. This is the camera, and for the flow I need some kind of pressure difference. So this pump is creating the pressure difference, and the sample is kept here. The sample is kept here. So I'm just applying a pressure difference to a crystal. The crystal is flowing, and I can directly see on the screen what's happening, how it's flowing. Next,
This is
uh,
this is real time.
this is real time, yes. So that's the beauty, direct visualization in real time.
Okay.
So this is our lab. I think you can pretty much see what's behind me. So we are also building something cool. This is called an optical tweezer. So using optical tweezers here, you can almost like gods with the colloids. I can hold a particle, I can make it move, I can go somewhere, I can give it a kick. So I can launch a colloid at a crystal, I can, and then I can see how a crystal breaks. So if I just tear down a paper, I never know what's happening, how it's breaking. But if I just make the structure of the paper in colloids, and if I hit another colloid at it, I can just see how the breaking actually happens at a molecular level. And to do colloids, you also need some kind of, you need to do a bit of chemistry. So that's why we do the chemistry. Anyway, moving on. I think my screen froze. Ah, sorry guys, my screen.
You can share it again. No, it's fine.
Yeah, yeah. some of the problems solved using colloids are if I have a liquid and it's forming a crystal. So if I know the crystal has a BCD structure, so people is to initially thought that say, suppose my end goal is BCD structure, so it will always form a BCD structure directly. But people have shown that the structures actually evolve. So all sort of these structures are possible in between. These all are metastable structures. But the end structure is BCC. It doesn't mean that it will not form these other structures, HCP and FCC structures. So here that means my BCC structure. So at the end there are a lot of BCC structures, but at the beginning you can see that the crystallization actually happens via the HCP structures because it has the lowest energy.
Like, is it possible for like only for colloids this happens, or like other crystal
It
structures? Other...
see, it is basically colloids give you the F equal to ma for physics. So colloids will
Right.
tell you what are the rules of the game, how it's happening, and it's of course it will be true for molecular system because the free energy equation deals the same condensed phases.
Okay.
So also using colloids. So typically when we talk about physics, we'll talk about spheres. But if you look around, things are not always isotropic. And isotropy is always there, like your blood cells. They are of the shape of ellipsoid. So you can stretch a colloid to make this kind of structures ellipsoid, and then you can study their dynamics. Like you can see that if you have ellipsoid, they tend to stay together and form these kind of nematic structures where their orientation aligned up. Is it visible here? So they are lined up together.
Yeah.
Yeah. Also, if I have a pattern substrate, so here in the background, I have a square lattice and on which I can look at the diffusion of particles, how these particles are diffusing, randomly diffusing. So these are beautiful things you can do using colloids.
So we are using the pattern surface to, like, it is easy for detection.
No, no. So the problem at hand is that I don't know how my particles will diffuse at a pattern surface. I cannot use an atomic system because I cannot see their motion. I will use colloids. I will make a pattern surface and then I'll put
Okay.
colloids on it and I will just see how they're moving and I can use this using a software, I can track their motion.
I see. Yeah, yeah, yeah.
Also, like I told you about optical tweezers. So it happens that using a sharply focused laser beam, you can hold a particle. So here you can see a demonstration of optical tweezers. So you can see that this is a sharply focused laser beam. My screen again froze. So you can see that this is a sharply focused laser beam and I'm able to drag the colloids using this beam only. So like so what I can do is that I can have a DNA strand, I can attach them to colloids, and I want to study the elastic properties of the DNA. How much force does it take to break? What is its elastic response? So I can take two optical traps and using the laser beam, I can just shift the laser beam and I can see what is the elastic response of a DNA or a polymer. So colloid can make your life easier. I don't know why it's
Yeah.
freezing. I don't know why it's freezing repeatedly.
Due to network issue, maybe.
No, no, it's a system issue. So, like I said, the work that I did in my first year, it was that you can see that these particles are doing random motions, seemingly random motion. They are not caring about what the other particles are doing. Is it? They are doing the random motion. But what I was able to show is that, so each particle, if I just plot the displacement of each particle, it's, if I just plot the probability distribution, like kahan pe jata hai wo particle. If I have two particles here, and if I ask the question, why is the particle going? It has a probability of going in all of the direction. And that's why the distribution is Gaussian. Now I'll ask the conditional probability. Since I have the trajectories of the particle, I've located the particle, I've tracked the particle, I can ask the question, suppose I consider two particles, if the particle moves in this way, what this other particle is doing? Although these systems are that they are not talking to each other, the interaction is hard sphere interaction. I see that if the particle moves in this way, that particle also goes in this way. So there's some kind of talking, some kind of cooperation between the particles here. But now I can ask the question in a different direction. If the particle goes in this way, what happens to that particle? So in that case, then like एक नीचे जाएगा, एक ऊपर जाएगा. Now nobody is asking, preventing me to ask the question at separation very close, at very close separation. So if the two particles are very near by each other, one particle goes down there, other particle comes here to fill the void. Now we'll be asking, ये क्या बोल रहा है? What are the implications of this? The implications are, it's actually, since these particles are in solvent, as a particle moves, it displaces some water. It displaces some of the solvent. So a particle यहाँ पे, it moves, it creates a void here. So solvent from the other places come to fill in the void, and it creates a dipolar flow profile around the particle. So if a particle moves from this point to that point, so it will create a flow profile. Flow profile are just like your electric fields. It will create a field around it, such that if there was a particle, अगर एक particle यहाँ पे होता, it would have felt a force in this way. यहाँ पे होता तो in this direction, and अगर यहाँ पे होता, it would just come here to fill the void. And I will not go into technical details of the implications. So the implication was that it led to the breakdown of something called a Stokes-Einstein relation. So Stokes-Einstein relation tells that the viscosity, like viscosity just means how thick a liquid is. Honey is more viscous than water. Cough syrup is more viscous than water. Okay, बहुत thick होता है. It's very hard to move in. If you just put your hand inside honey, it will be very hard to move. If you drop a ball on water and honey में ज़रा time लगेगा उसको नीचे जाने में, because it's thick, it's viscous. So Stokes-Einstein relation says that there is a direct coupling between viscosity and diffusivity. Diffusivity means that how fast a particle can move. So in a viscous medium, it's very hard to move. So Stokes-Einstein relation tells that the viscosity is inversely proportional to your diffusivity. But we find that, and it is expected to be valid for liquids, we find that it breaks down in case of 2D fluids, but it doesn't break down in 3D fluids. So it was an unsolved problem in literature. We took that problem and solved it using colloids. We provide a mechanistic route to how and when this Stokes-Einstein relation will be violated. Now one may answer, Stokes-Einstein violate हो गया तो क्या हो गया? What's the big deal in that? Big deal is that it's hard to so if I have a direct coupling between the viscosity and diffusivity, viscosity is macro parameter. I can measure it in a lab easily. So just by knowing the viscosity, I can comment on the diffusivity. Why do I need the diffusivity? Perfume देखा होगा ना? So if you just spread a perfume, it takes very less time for it to spread.
Yeah, in an instant.
Yeah, it's because diffusivity is very high. Okay, so a direct relation between viscosity and diffusivity is not only useful for academic purposes, also useful for industrial and practical purposes. So we now know that Stokes-Einstein relation violated, and we wanted to see if it could be fixed. Can I do something? to fix the Stokes-Einstein relation, the coupling between viscosity and diffusivity, the coupling between how fast my particles are moving and how thick my liquid, how dense my liquid is. So what we did is that we considered two particles and we looked at the displacement. So this part, suppose these two particles move from here to here, and this is my displacement of the center of masses. We looked at the displacement along the motion of perpendicular and in a direction perpendicular to the motion of the center of masses. And if I just look at this direction, it means it's just a changing the frame of reference. So I was able to recover the Stokes-Einstein relation just by changing the frame of reference. So it means that the physics remains same. I just have to change my view. So
Oh,
yeah, so I've already explained this. Like we're trying to figure out what happens if you just add some impurities in your system and how will my crystal look like? Why will crystallization happen? And this is a setup that I'm currently working on. We're trying to build an optical tweezers so that I can trap colloids. I can make them move at my will.
oh,
So
okay. Like we have a question on optical tweezers only. So he has asked, Pulkit has asked that do the optical tweezers work on radiation pressure?
yes, exactly.
So if any more
So
questions,
so
do
so
ask.
so it's just like if I it's just like if I put a uh, ping pong ball. If I have a running water, if I just put a ping pong ball, so the ball will try to center it around the water flow. So it's just the gradient of the radiation pressure that is in the play.
Okay. Like if you want to ask question, you can directly ask to on the mic also.
Yeah.
So don't hesitate to ask question. Okay. One more question I have. What is the most influencing factor of diffusivity?
Uh, what is the most influencing? That one example I gave is the परफ्यूम case. Second thing is impactful is that suppose मेरे को सर दर्द हो रहा है, ठीक है, and I will go and take some kind of painkiller. If the diffusivity is more, it will take less time to diffuse into my body and give relief. So medicines are always designed such that it has higher diffusivity. So it's important in drug delivery and all. Did I
Okay.
make it clear?
Yes. You can go ahead.
Go ahead, आगे कुछ है ही नहीं यार, फंडिंग इंडेक्स दिखा रहा हूँ.
Okay.
Questions पूछो.
So so you can open your mic and ask question to Nomenda if you have any. I have one question.
Yeah.
Like, uh, it's soft matter is like multi-dimensional field. Like we
It's a
have to know the
dimensional element.
chemistry. We have to know the biologies to know the
Physics, most importantly, physics,
yeah.
and a bit of computational because we deal with statistical mechanics. So it's a billions and billions of statistics that you have to handle, terabytes of data in one experiment. It is almost a terabyte of data in just one experiment.
Yeah. Like, what about the like? What is the difference? Like, does matters or does like the things we study, the fluids that we study here in in physics, they're different from that in chemistry, you know?
Sorry, I didn't exactly get you.
Like how is the study different? Like what we study here and
Soft matter is not. I would not say it's very tough. It's perhaps the easiest one. It requires you to use your intuition and common sense, and you need to know the breadth of your subject. So you need to know almost. Uh, you need to have knowledge across multiple disciplines. You need to know classical mechanics. You need to know thermodynamics. you know statistical mechanics, you need to be an expert in those fields, but you should have your common sense on. बिकॉज अभी देखा ना कि पार्टिकल को ट्रैक करना, सेंटर ऑफ मास की पर्टिकुलर में देखना, these are just intuitions, and it has the capability to answer the one of the unsolved questions, what is life, how a collection of atoms when arranged in certain way can give you something so meaningful, so living like.
Yes. Like it's still the research is going on.
Yeah.
So like we can expect that like we have one more question. Let's address that first. So Abhishek has asked, does the depletion interaction just exist between particles and polymer?
Depletion interactions, when you say depletion interactions, so I have some kind of bunch of particles, colloidal particles, okay, and I will have smaller particles. So होता ये है कि okay, let me try to get something to show. So suppose these are my particles. These are not spherical, but assume that these are spherical particles, and I have small polymer particles. Suppose this is small polymer particles. So ये यहाँ पे जाएगा, ठीक है? इसके साथ ये जाएगा, एक और पॉलीमर इसके साथ रहेगा. Hope I don't break anything. इसके साथ रहेगा, ऐसे रहेगा. ये एक पॉलीमर है, इसके साथ है, ये इसके साथ पॉलीमर है. So what will happen is that, so this is the state of the system. What happens if the two particles come together? क्या होगा? सारे polymer, जो छोटे polymer से, they will go out and they will get more volume to explode. So the number of microstates will increase, and as a result, there will be a geometric attraction between the two particles. So it's just geometric. It's just due to entropy. So let me draw it. I don't think I made myself clear. So okay. Give me a second. Let me pull out some image that will be helpful.
Yeah.
কোনো নাই এতিয়া can you just comment section to problem
I'll just share my screen. So Abhishek, are you working on soft matter?
You can open your mic. You can talk. You can talk directly on this mic
So
also.
this is my particle. These are my particles, and they have a bunch of small polymers around them. So it just happens that two particles are closers. These particles will be freed up. They will go in the extra spaces, and they will feel an osmotic pressure towards them. And it's just because of this overlap volume, we're getting some kind of attraction. So to answer your question, the depletion interaction is between the bigger particles. It's not between the smaller particles and bigger particles, not among the smaller particles. It's among the bigger and bigger particles. So did I answer it correct? Are you happy with the answer?
So do you have any more questions?
So if anybody if you want to do an internship here, you can just write to our lab. So we have a few open positions. Just advertising.
Is there any more questions? I think there are no more questions, so
Okay. Okay.
we can just end.
Okay.
So thank you
Nice.
very much.
Yeah, it was a nice session. Like I didn't expect like these kind of questions to depth. These are not just questions on surface level.
Yes, yes.
Yeah.
It was the session was very like insightful. Like I didn't know many of the things, and the audience also got to know many of the things. So sure, everyone has loved it. We will like you to have on the campus here soon. So
Yeah. Cool. I will try.
yes, yeah. So thank you very much once again from the team of Insignis.
Yeah.
We'll you can just finish your ending remarks and we can end.
So thanks all. If I just come to campus, I'll try to meet a few people across the disciplines. Like it's very important to network in not only in corporate sector but also in scientific community, and that I realized it a lot later. So it's very important to network. So
Yes,
if I come, I will try to build some connections.
sure,
Good.
sure.
Yeah.
So we can end then.
If anybody has any questions, so you can just
Yes,
mail me. You can just mail me.
you can share
Uh,
your email here.
Yeah, Abhilash can share with them. I will share the mail on the WhatsApp group as well. Sorry, it's the wrong mail. Second one is the correct one. Okay. Bye bye.
Okay then, we will end.